How to switch an antiferromagnet. Synopsis. September 4th, 2025. Physics 18, S111. Two primary mechanisms govern the reversal of antiferromagnetic domains. Scientists have pinpointed which one dominates under specific conditions. Antiferromagnets consist of two sublattices whose magnetic orientations oppose each other, cancelling out their effects. However, if one sublattice breaks inversion symmetry, flipping both creates a configuration with distinct transport properties. This duality opens new avenues for storing and processing information. Martin Jourdain of Johannes Gutenberg University Mainz and his team discovered two flipping mechanisms operate at different timescales. Their findings challenge prior assumptions about the flipping process. Researchers typically apply spin-polarized currents to flip antiferromagnets. These currents induce sublattice magnetizations to twist via spin-orbit torque, SOT. Yet, recent studies reveal that prolonged current pulses can cause mechanical strain from resistive heating, snapping sublattices into new configurations, whether or not SOT is involved. Jourdain and collaborators tested these mechanisms in thin films of Mn2Au, a material prized for its triply advantageous properties. It's a conductor, its manganese sublattices break inversion symmetry, and its gold sublattices host electrons with strong spin-orbit coupling, making them highly sensitive to SOT. The team differentiated the mechanisms by analyzing magnetic domain patterns after applying current pulses with varying orientations. SOT-induced flipping depends on current direction, while heating-induced flipping is orientation independent. They found that 2.5 nanosecond pulses produced SOT patterns, whereas 100 nanosecond or longer pulses revealed thermomagnetoelastic patterns. Jourdain notes that prior experiments used currents longer than 1 microsecond, placing them in the latter regime. Controversy discussion. But here's where it gets controversial. The distinction between SOT and heating-induced flipping is not always clear. Some argue that the mechanical strain from heating may actually enhance SOT effects, blurring the lines between the two mechanisms. Others suggest that the timing of the flipping process could be influenced by factors beyond just pulse duration, such as material imperfections or external fields. What's more, the choice of material, Mn2Au, raises questions about scalability. While it excels in lab settings, its real-world applicability remains uncertain. Could this material pave the way for next-gen memory devices? Or might its sensitivity to SOT limit its use in certain applications? Final thoughts. As we explore the future of data storage, the ability to control antiferromagnets with precision becomes increasingly vital. Whether through SOT or heating, the next frontier lies in understanding how these materials can be manipulated to meet evolving technological demands. Who's ready to dive deeper into the science behind this fascinating phenomenon? Let's discuss in the comments. Do you think the distinction between these mechanisms is critical, or is there room for innovation in their interpretation?